Here's one more application of the law of cosines. This is a problem we did a couple days ago on a previous video. I think I showed it to you where sometimes there are two different triangles that satisfy a problem. This was a case of where x was 35, little x was 8, and y was 10. It turns out there are two different triangles. This was the so-called two sides and a non-included angle situation, and where you often have two different triangles. The 8 could have been placed this way, or the 8 could have been placed to the inside going this way. And so as a result, you have two different triangles, a big triangle and a small triangle. And last time we worked it out, we did the law of sines. We applied it to the big triangle first and found all the missing pieces, and then we used a little bit of geometry along with the law of sines to solve the skinny triangle. Well, it turns out you can actually come at this problem using the law of cosines. It's a little unorthodox, but it's kind of a neat application, and so I'd like to share that with you. What you could do here, since you've got an angle and an opposite side, okay, we could apply the law of cosines, and it would look something like this. It would be 8 squared equals 10 squared plus z squared, because we don't know how long this other side is. So it's going to be 8 squared equals 10 squared plus z squared minus 2 times 10 and z, and then cosine of, and then across from the 8 is a 35-degree angle. So this looks a little different, but if you think about it a bit, you realize, okay, well, there's only a single variable here, z. So anytime you have a single variable in one equation, this is something we should be able to solve. And so now we're going to go through the steps and see what happens here. You'll have 64 equals 100 plus z squared minus, and now all of this can be cleaned up a little bit. If we do, see, 2 times 10 times cos 35 times cosine 35, and we get about 16.38. I'm going to call it 16.38 z, 16.38 z. And you start to play around with it a little more, and at some point you realize this is really just going to be a quadratic equation. It's going to be z squared minus 16.38 z. Let's see, 100 minus 64, I believe, is plus 36. And you have a lot of ways to tackle a quadratic equation. The easiest one in this case will probably be to use the quadratic formula. So z equals, let's see, negative b, so 16.38 plus or minus the square root of, okay, we've got to go b squared, so 16.38 squared, 268.30, just round it a bit, 268.30, minus 4 times 1 times 36. So 4 times 1 times 36. 4 times, I don't need the 1, 36 would be 144. All over 2a. Okay, so it's going to be a real answer. So 16.38 plus or minus, and then I'm going to go ahead and work out the root part right here, 268.30 minus, I think it's 144, that answer. Then I'm going to take the square root of that answer. So about 11 point, I'll call it 11.15. 11.15 over 2. So taking that a little further, so this is z equals, and so now I have two cases. 16.38 plus 11.15, and then divide that answer by 2. So I get about a 13.77. Or the other option is if I go 16.38 minus 11.15, and then divide that by 2, I get about a 2.62. 2.62. Now you'll have to go back to the previous video to see if these were, pretty good measurements for z that we got from before. For now, I'm just going to go ahead and check with my ruler. So 2.62 is the shorter z. So that looks pretty promising, a little more than 2.5. So 2.62 looks pretty good. And then along the longest side here, let's see, that's 12. So on mine, it's almost 14. It's a 13.77. Seems very reasonable. So I'm liking these answers given the picture that I've drawn here. And so I leave it for you then to go back and check these with the previous video to see if that's what we got for z. Now once you have these, okay, you can then go through and find the other missing pieces using the law of sines. So again, this is a nice little example of using the law of cosines. It leads you into a quadratic equation which you can solve and then find out the two missing pieces, the long z and the short z, and then thereby find the rest of the components of each triangle. So thanks again for watching.